welcome to GemChem. Now today's video is on chemical kinetics part 6 video, and here we are going to deal with kinetics of complex reactions. Now the complex reaction under consideration is reversible or opposing reactions. Now before starting, already 5 videos on chemical kinetics are being uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present about this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. We are going to deal with basically two types of reaction where these concentrations of the product in first case will be 0, and in the next case we will see that the concentration of the product is something when the time is taken as 0. So if we begin with type 1. We will derive the expression, rate expression and other concentration factors also. So in type 1 we have a reaction where A reacts in a reversible manner to give B, and the rate constant of forward reaction is Kf and the backward reaction rate constant is Kr. At T equals to 0, the concentration of A is A0 and the concentration of B is 0. At T equals to time T, the concentration of A is equals to A0 minus X, and here concentration of B is X. Now what is X? X is the extent of reaction and we have already discussed it in details, right? Now this can be written as like this. This is equivalent to AT. This whole thing is equivalent to AT and this is equivalent to BT, that is concentration of B at time T. Now we know that next step is to do the derivative of the extent of reaction. So our rate is equals to dx by dt, right, which is equals to Kf is naught minus X minus Krx, and this is our equation which is numbered as equation 2. Now we will consider this as equals to minus dA by dt, as A is the reactant and it is equals to dB by dt, and we know the concentration of dB to be as dx by dt, and this can come as the above one, that is Kf A0 minus X is equivalent to concentration of A at time t minus Kr, and the X is the concentration of B, right? So this can be now modified, and this is our equation 3. Next, at equilibrium we know that dx comes to be as dx by dt, more specifically comes to be as 0, right? So at equilibrium we can write dx by dt. All steps are being mentioned in the previous videos in details, right? So here we will do a fast job. So here we can write it as x equals to x equilibrium. So ultimately what we can write is, we can replace the value of dx by dt with the original value, which is Kf in bracket A naught concentration minus x equilibrium minus Kr x equilibrium equals 0, and this is our equation 3. And correct this one, this is taken as our equation 1, this equation. So this will be our equation 1. Next, after getting equation 3, we can from here derive the value of Kr, which is equals to Kf A naught minus X equilibrium by X equilibrium, and this is our equation 4. Now we need to substitute the value of 4 in equation 2. So substituting value of 4 in equation 2. Now what is our equation 2? Let us see again. This is the equation 2. So we will substitute the Kr value here. Now what comes is this one, that is dx by dt equals to Kf A naught minus X, and we have replaced already Kr, so we get Kf A naught minus X equilibrium by X equilibrium, and we have another X equilibrium at the outside. So this is our X. Here, since this is only X, so we will write it here only X. Now this simplification is required. See here Kf, and here it can be written as A0 by X equilibrium multiplied by X equilibrium. So we are using X equilibrium up and down, minus X and minus Kf A naught by X equilibrium minus 1 X. If you focus on these two terms, that is this one and this one, these two will get cancelled out. So what we are left with is dx by dt comes to be as Kf A naught by X equilibrium minus X. This is what comes, and this is our equation number 5. Next we will see this equation in the integrated form. Take X up and down 0, dx by X equilibrium minus X equals to Kf A naught by X equilibrium integration 0 to t dt, and what comes is like this, minus ln X equilibrium minus X 0 to X equals to Kf A naught concentration by X equilibrium t. From here we ultimately get this expression, that is ln X equilibrium by X equilibrium minus X equals Kf A naught concentration T by X equilibrium. Now if you focus on this equation, this is equation number 6, and what are the things which are unknown? This X is unknown, this Kf is unknown, and this T is unknown, right? So once we find the Kf value, then we can easily obtain the value of Kr. Next step is that from equation 3, we can write it like this, that is A naught by X equilibrium is equals to Kf plus Kr by Kf. Let us see again equation number 3. This is our equation number 3, and from here we can directly write this equation, what we get as equation number 7. So let us write this as equation number 7. Now we will use this 6th equation and 7th equation together and obtain another value, that is using equation 6 and 7 we get ln X equilibrium by X equilibrium minus X, and this comes to be as Kf plus Kr multiplied by T. This is one of the most important equation for our reversible reaction. This is our equation number 8, and simply this is a first order reaction with respect to A naught. Here A naught is being replaced by X equilibrium and K with Kf and Kr. See, we have already seen the first order equation like this, that is ln A naught by A naught minus X equals to Kt. So here K is Kf plus Kr, whereas this A naught is X equilibrium. Now we will see the different forms and the different techniques to obtain the Bt and At. If you focus now, we have obtained different equations like this: X equilibrium by X equilibrium minus X equals to e to the power minus Kf plus Kr T. What we have done is, we have taken antilog in both sides. So now what we have obtained is minus 1 minus X by X equilibrium equals to e to the power minus Kf plus Kr T. Okay. Now A and B at any time t can be obtained from here. So let us finally derive the formula. From here we get X equals to A naught Kf by Kf plus Kr 1 minus E minus Kf plus Kr T. This is the value of X which is being obtained right now. Now we will see the value of X equilibrium in the next step. So Kf A naught minus X equilibrium equals Kr X equilibrium, we have already seen. So from here we can write X equilibrium equals to A naught Kf by Kf plus Kr. So ultimately we know that concentration of B at T time is X, right. So in the previous slide we have already seen this is the value of X which is being obtained. We will just substitute the value here, A naught Kf by Kf plus Kr, and in brackets 1 minus e to the power minus Kf plus Kr multiplied by T and close brackets. Now we will derive the expression for At. At equals to A naught minus X, and A naught remains as it is and X is replaced by A naught Kf by Kf plus Kr, and in the brackets 1 minus e to the power minus Kf plus Kr T, and these brackets are then closed up, right. So from simplification what we get is A naught by Kf plus Kr multiplied by Kf, and this comes to be as Kr by Kf plus e to the power minus Kf plus Kr multiplied by T, and this is our equation number 10. And ultimately we have derived Bt and At simultaneously. Now we need to find out the equilibrium constant. So equilibrium constant. Here equilibrium constant means that it is K equals to B equilibrium by A equilibrium, and this is equals to X equilibrium by A naught minus X equilibrium. So we know that at T infinity we reach equilibrium, right. So B equilibrium comes to be as like this, that is B equilibrium equals to A naught Kf by Kf plus Kr, and this is our equation number 11, whereas A equilibrium comes to be as A naught by Kf plus Kr here, and 12, right. Now we will just put it up and down of K. So K will be Kf by Kr. This is our ultimate equilibrium constant. And we need to draw a graph showing that opposing reaction is being taking place. So in this coordinate we will take concentration, and in this coordinate we will take time. What happens is concentration of A decreases like this. So this is our A, and concentration of B increases like this. So this is our B, and this is the ultimate graph of this. Instead of time, you can also get the coordinate like this, Kf plus Krt. This is the coordinate. Suppose if given like this, that is Kf by Kr is equal to 2. What does it mean? It means that concentration of B should be twice of A. Remember this. This is the pattern to understand the concentration. So this was type 1. Already derived these equations for type 1. Right. So for type 2 reaction. In the type 2 reaction, what happens is that there is an initial concentration of the product present in the medium. So in type B, we have A undergoing reversible reaction with Kf as forward rate constant and Kr as backward rate constant, and this is B. At time equal to 0, we have A concentration as A naught and B concentration as B naught. At time t equals to t, we have the concentration as A naught minus x, and here B naught plus x, and we have already seen x is the extent of reaction. Here dx by dt will be equals to Kf A naught minus x minus Kr B naught plus x. Right. Now at equilibrium, we know what happens is dx by dt is equals to 0, right? Dx by dt is equals to 0, and x is equals to x equilibrium. So from here we can derive that Kf A naught minus x equilibrium is equals to Kr B naught plus x equilibrium, and this is our equation number 1. From here we can write Kr is equals to Kf A naught minus x equilibrium by B naught plus x equilibrium. From here again we can get dx by dt. We will substitute the value of Kr in the dx by dt. So Kf A naught minus x minus Kf A naught minus x equilibrium by B naught plus x equilibrium multiplied by B naught plus x. And on simplifying this whole part, that is particularly this part, what we get is dx by dt on simplifying is that Kf A naught plus B naught by B naught plus x equilibrium, right? And here x equilibrium minus x. This is the value of dx by dt. Now we need to integrate it. So we will write integrating what we get is like this: from 0 to x dx by x equilibrium minus x equals Kf in brackets A naught plus B naught by B naught plus x equilibrium, and here the integration is from 0 to t dt. The equation which comes is like this: ln x equilibrium by x equilibrium minus x equals Kf A naught plus B naught divided by B naught plus x equilibrium t, right? And this is our equation 2. Now from equation 1 what we get is like this: Kr by Kf equals to A naught minus X equilibrium by B naught plus X equilibrium. And this is arranged like this, that is A naught by X equilibrium minus 1 by B naught by X equilibrium minus 1. We are taking X equilibrium at the downside of A naught and B naught. It can be now written as Kr B naught by X equilibrium plus Kr equals to Kf A naught by X equilibrium minus Kf. We will take Kf and Kr in one side. So Kf plus Kr comes to be as Kf A naught by X equilibrium minus Kr B naught by X equilibrium. And this is ultimately 1 by X equilibrium Kf A naught minus Kr B naught. X equilibrium from here comes to be as Kf A naught minus Kr B naught by Kf plus Kr. If we go from equation 2, we see that A naught plus B naught divided by B naught plus X equilibrium comes to be as A naught plus B naught divided by B naught, and X equilibrium we have already derived right now from here, so we will just substitute it. So this will be Kf A naught minus Kr B naught divided by Kf plus Kr. This comes to be as A naught plus B naught by Kf B naught plus Kr B naught plus Kf A naught minus Kr B naught, and what we are left with is 1 by Kf plus Kr. So we have here 1 by Kf plus Kr. If you try to cancel out, then you will see this and this cancels, and what we are left with is this one, that is A naught minus B naught, and in the downside we have Kf A naught minus B naught, and this value, that is here we had 1 by Kf plus Kr, that is this was in the downside here, so it will be below, right? So it will go upside, so we will get it like this, that is Kf plus Kr. As you can see, this and this cancels, and what we get is Kf plus Kr by Kf. If we just substitute this value in the equation which we have already seen for ln, that is this equation, we get it like this, that is ln X equilibrium by X equilibrium minus X equals Kf plus Kr by Kft. This Kf cancels, and we get ln X equilibrium minus X to be as Kf plus Kr multiplied by T, and this is our equation. This is our needed equation for this particular type 2 reaction, type 2. And now we will see the 3 types of graph for these opposing reactions. First type is that when K is equals to 1, that is equilibrium constant is equal to 1. This is the concentration bar and this is the time bar. Now if you consider the reactant, then reactant will come like this, go down like this. Similarly, if you consider the product, then the product will come and meet it here at this end in the same way. In the same line, these two will meet. Okay. Next case, when you consider that K equals to 2, then what happens is, here we find that the product and the reactant is somewhat showing different way. So the reactant will go down very fast and the product will go up very fast like this. But the difference is little more. In case of K equal to 3, when you see K equal to 3, you will observe that this particular graph will show same type of thing, but the gap will be more. If you see this is the product, it will be here, and if you see the reactant, it will go down like this, and this gap has increased. So this is for K equal to 3. So we have already seen for type 1 as well as type 2 for opposing reaction and also the graphs involved in it. So this much for today. In the next video, we are going to deal with parallel reactions. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.